This is the answer for readiness check 6, which first asks, what will a loop closure do to the above system? Well, the open loop transfer function, the OLTF, is 1 over S squared. So that's the OLTF. And we see it plotted here with a minus 40 dB per decade log mag slope at an angle of 180 degrees, minus 180 degrees, corresponding to 1 over S squared with S equals J omega. If we were to close the loop on that, the closed loop transfer function is shown on the root locus. And we see the loop closure CLTF for a gain, a root locus gain, equal to 1. And it shows you that with boxes. So we have a box here at J omega, and we have a box here at minus J omega. So if we were to draw phasors up to that, this phasor I'm drawing right here would be J omega at an angle of 90 degrees. And the one, its sister, would be minus J omega at minus 90 degrees. Now the metrics that predict this neutral stability or near instability, if I were to go to the crossover frequency, which is shown here at 1, and then come down from the crossover frequency to read the phase angle, the phase margin, which sometimes is used symbol phi PM, equals 180 degrees plus the phase angle at crossover. So the phase angle at crossover is minus 180. So 180 minus 180 is 0 degrees. So that means I have no phase margin, which you can see here. I have no phase margin, and that's evaluated at 1 radian per second. So put the gain margin in your pocket for a second, because actually the gain margin is not defined for this particular system, but you'll have to hold off as to why for now. Now to plot the root locus, we know that we pick trial points such that the OLTF equals 1 at an angle of plus or minus 180 degrees, right? And this was going to give us points that are on the root locus. So we have to pick our trial point to give us plus or minus 180 degrees. Well, since we have two poles at the origin, and if I pick my trial point up the J omega axis, then these phasors, LP, we'll call that LP1 and LP2, they both equal 1 angle 90. And so I see that the root locus goes up the J omega axis as the root locus gain is varied. And the root locus gain equals the product of LP1 and LP2. In other words, we know from the magnitude condition that the root locus gain, if that was being varied, a KRL up here, then the root locus gain would have to be the product of LP1 and LP2 to give us a magnitude condition of 1. Question 6b says we should drive this system with your actuator from lab 1. So I've taken the actuator here to be 15 over S plus 15, driving my system. In MATLAB, my shorthand notation gives me a 1 over S squared. I'm holding a washout of S over S plus 5, and my actuator is 15 over S plus 15. So my first open loop transfer function is G times the actuator. I'm leaving the washout out right now. So if I were to show my OLTF1, which is just the actuator, I get 15 over S squared times S plus 15. So what happens when I close the loop on that? Then on the left hand side, my my OLTF, which is equal to 15 over S plus 15 times S squared, will have a break at 15. And you can see that right here, where I go from minus 40 dB per decade then to minus 60 dB per decade, and that should occur right around 15. Because the phase kicks in going another 90 degrees down from minus 180 to minus 270, that phase angle kicks in at 1/10 the break frequency. So if the break frequency is 15, if this is omega B of 15, then at 1/10 of that, the phase angle will start to decrease by 90 degrees more. Okay, and at 10 times omega B, which would be over here, so this would be 10 omega B for the actuator. If I were to connect that with a straight line, I would connect 1/10 omega B, 1/10, the break frequency of the actuator, with 10 times, then at 45 degrees the phase curve would match. But you see that the phase curve itself here, that phase curve itself is going to give me a negative phase margin. So if I were to compute my phase margin, so my phase margin is minus 3.8 degrees at 1. That means the system's unstable. In a closed loop, if I close the loop on this open loop system, then my CLTF should show roots going unstable, and indeed it does for a gain of 1. And here, of course, is the time response. Now remember, the SISO tool, when used this way, is assuming everything is happening in the forward loop, in this forward loop. So we could call this a G forward. And when you're using SISO tool, unless you specifically go in and tell the SISO tool otherwise, it will assume that everything is occurring in that. Now for part 6C, we're going to put a washout circuit into this system, which is equal to S over S plus 5. Now it's going to have a washout gain, but initially that gain will be 1 because that's the gain that's going to be varied in the root locus program. In other words, we're going to vary the gain in the feedback path. So my second OLTF will be equal to the actuator times G washout. The closed loop transfer function, when I close the loop on this second system, is going to be equal to a numerator, which I have to remember because the root locus program will not help me with that. And that numerator is going to be the K that comes in my G, and since my G is 1 over S, that's just 1. The K for the actuator, and since my actuator is 15 over S plus 15, the K actuator is going to be 15. So this Kg is going to be 1, and this is going to be 15. Then the numerator polynomial in S of G is going to be 1, because there isn't any polynomial of S and G in the numerator. It's just 1 over S squared. And the denominator of H of S is the polynomial in the denominator of H. And I see that that's going to be equal to S plus 5. So the polynomial in H is given by S plus 5, and that comes from the H. Now that closed loop transfer function numerator is going to be over the roots, right? And the roots are going to come from the root locus, and those root locus will be conditioned on a given value of root locus gain. Now we know that the SISO tool, unless I fix it, actually the SISO tool will vary the gain in the numerator, right? And then so we will have to put the correct numerator in when we get the roots from the root locus. So let's go look at SISO tool here, and I've got the open loop transfer function 2, and that equals, up here you can see I had the actuator times G times the washout. My washout is shown as S over S plus 5 in the shorthand form, and the second open loop transfer function is given by 15 over S times S plus 5 times S plus 15. That's the open loop. So I do SISO tool, and so I see that my OLTF, my crossover frequencies here is at 0.2 radians per second. That would be this fellow right here. So that's at 0.2. And I have 90 degrees of phase margin, which is good. That means my system is going to be stable. And if I look at my phase margin, of course my phase margin and a phase angle of crossover looks like it's 90 some degrees. So my phase margin is 86 degrees. So I have plenty of phase margin. That means my system's going to be stable. And if I look over here on my closed loop system, if I were to close it with a gain of 1, my root locus gain of 1, and again, remember the SISO tool is closing that in the numerator, my roots are all stable. So my closed loop roots are stable. So I have a stable system, and if I look back at my closed loop transfer function for this situation, I can take those roots that come from a gain equal to 1 and put them into this transfer function with that numerator, 15 times s plus 5 in the numerator, and that will give me the closed loop transfer function for this system. I also can get the gain margin now. The gain margin is well defined. Notice it gives me 40 dB. So to get the gain margin, we go to the point where the phase margin curve crosses 180. And we go to the 180 point, and we draw a line straight up, which MATLAB does, or Sizo tool does for us. And we can see then that the distance we were below, right, the distance we're below the 0 dB line is the positive gain margin, right? So in other words, as long as I'm below the 0 dB line, when I'm at 180 degrees, what I have to add to the gain margin to get to 0 is going to be my gain margin. So you can see it directly off the graph. The gain margin and the phase margin, and I want the closed loop transfer function, which we'll call CLTF2 for the second loop closure with the washout. Then I have G over 1 plus GH, the shorthand version. And you notice that at 15 I have s plus 15 in the numerator and I have s plus 15 in the denominator. This is because of numerical properties of MATLAB. So whenever you see that, whenever you see the same numbers showing up in the numerator and the denominator, you can clean it up with a command called minreal. So if you just use CLTF equals minreal CLTF for 1 or 2 or whatever it is, notice how it will cancel that pull in the 0 at 15 for you. And then if you were to notice that the 15s are canceled, and I have a stable response. The other thing I wanted to show you was if you take the Bode plot of the closed loop transfer function, you'll get what's called, or you'll be able to determine what's called the bandwidth. So here is the closed loop Bode plot, and the bandwidth is defined as the frequency where the output falls 3 dB from the input. So assuming my input's at 0 for 1, then 3 dB will be approximately this area right here where I have my arrow moving. And the important thing is, this is a very important metric. We'll talk about it in class. But the important thing is that the open loop curve crosses 0 dB is a good predictor of the closed loop bandwidth. And that's what I wanted. That's the point that I wanted to make for this case. So these scales are, if you wanted Sizo tool to give you the correct transfer function, then at MATLAB you would have to call Sizo tool with the correct G, which in our case is G times G actuator. You have to call it with the correct G. And then in the system configuration box, the system you would go to the architecture system data, pick an H. You're going to pick an H. So now after you pick the H, you're going to browse and pick the washout. Then import the washout. Then you can close this, and you see that it has the washout in there now, and you say OK. So when you give it a step response to a step command, you're going to get the ramp that you had before, that you should get. However, when you vary the gain in Sizo tool, even after you do this, Sizo tool will vary the gain in the numerator. So if your gain is not 1, which it is here, then you could still have a difficulty with it. Okay, that ends this. Good luck.